Let me start by giving you a quick recap of what we have covered yesterday. Yesterday was the first lecture we had on deep learning, and we started with the history part. We explored MP neuron, that is Nicholas Pitt's neuron, right? And this was the elementary step the people have taken toward the journey of deep learning. We saw what is the artificial neuron, right? And this is a counterpart, or I should say, an analogy if we have to relate it with biological neuron, right? The whole intention is to come up with a system that can make decisions the way human cognition does, right? So it's very well established that whenever we have to take decisions, we rely only on our brain. We take the use of our previous experiences, we consolidate them together, and based on that we take decisions. So similarly, if we have to do it in deep learning, we have to make the use of artificial neuron, right? And later we'll see how we can combine this artificial neuron. So this artificial neuron is just a building block of deep learning. We have to come up with a way so that these neurons can interact with each others and create some sophisticated system, right? We also see how we make a decision like whether I should watch movie or not, right, with the help of artificial neuron. And we also briefly touched the mathematical intuition behind this, right? We related it with biological neuron, right? And we laid the analogy between the terms of biological neuron and artificial neuron. We said that uh, Nazma, if you're not talking, can you please go on mute?
Yeah, please.
Yeah. So dendrite of a biological neuron is somewhat similar to the inputs of these artificial neuron, and the way we have synapse in our nerve cells, similarly we are having weights in artificial neuron, which is in a way determines the strength of connection between the uh, input inputs, or I should say in a broader term, it shows the strength of association between different neurons, right? So for example, if you have to make a decisions and that decision is based on the multiple factors, if there's a one particular factor which is very important for you, right, so you'll assign a higher weight for that particular factor, right? So there is a part called soma in biological neuron. Counterpart of that is this part, which does the aggregation of our input and weight, and it applies certain function to it. We are yet to see what that function is, and the final output is what we consider for making the decision, right? We read about these two people, Walter Pitts and Warren Bucola. These two are the people who proposed the first model of artificial um, neuron, right? And these were the foundation block for deep learning. And this is really important. This slide is very important. I mentioned that whatever study that we'll be making further from today onwards, all these studies we have to map with one of these two jars, right? So if I have to come up with any model, a learning model, there are primarily 6 characteristics associated with it. One is the data, the other is task, model, loss, learning, and evaluations. And we opened the first chart, that is the model part, right? And I told that a model is nothing but it's a mathematical representation of relationship between multiple features, right? We checked about the MP neuron model, right? The mathematics behind that, right? And yeah, so this is the part from where we have to start today. So we opened the model jar yesterday. Now let us close that model jar and open the another jar, which is the data jar. Okay. So now we have to understand what kind of input variable our model is capable of handling and what kind of output uh, data it would yield, right? And I think this is briefly we covered yesterday also. right? So on continuing that, let us take an example, right? So you must have seen cricket in some uh, time, like in past, and there are situations where an umpire declares out to a batsman, right? LBW out. So how does an umpire make that decision that whether the batsman is out or not? He considered certain factors like, he'll check if the ball is placed on line in line or not. If it is in line, then we represent it as one. If the impact is there or not, yes. If it is yes, then he goes to the other criteria, checking the missing stump or not. If it is not missing, let's say that it is a one. And if all the necessary criteria are matched, in that case the umpire will keep out, right? So the way umpire is making this decision, the same kind of decisions we can also make by using MP neuron model. Okay, and how do we do how would we do that? We'll come to that part a bit later, but for now just understand the hypothesis or the primary function of MP neuron, and that is we have the multiple input, right? For example, here we are dealing with three input features. These are called the input features, and this is called the target feature or target variable. So what we do in MP neuron is whatever input feature we are having, whether it is 0 or 1, we first of all add all those input uh, features, right? And we'll check the summation. If the summation is more than some threshold, in that case your target output will be 1, else it would be 0, right? And what would be that threshold? That threshold is something which we get to know after learning. So that is a part where learning comes in, right? But the hypothesis function is pretty straight, right? We deals with a lot of Boolean input. We take the Boolean input, we simply do the summation. Then we check if the summation is more than a certain threshold, then we say that the output will be 1. If it is below that certain threshold, we say that the output will be 0. Very simple, it's very primitive, and it's a very elementary concept in deep learning, right? Is it clear? Is it clear? Please, I'm waiting for your response.
Yes.
Cool. Now, let's say that, so here you see all the input features were binary. It is either 1 or 0, right? But in real life, it may not be a situations where you'll always be getting a binary input. You can have a real input also. For example, you want to purchase a phone, right? So whenever we think of purchasing a phone, there are a lot of things we think, right? For example, we check whether the phone is recently launched or not, how old that phone is, whether it is launched 1 month back, 2 months back, 3 months back, right? So in this case, this variable can take an integer value, right? It can be 1, 2, 3, 4, anything. So here, if I have to still apply a MP neuron in this particular case, how would I do that? Right? So one way of doing is we can binarize our data, right? Here, although my data is not in binary form, it is an integer form, but still I can make it binary, right? Here I'll just do some feature engineering. If I'll just say that whether the phone launch within 6 months or not, right? If it is launched within 6 months, I'll say that it is 1. If it is launched not within 6 months, I'll say it as 0, right? So whole point is, even though if we don't have the binary data, we can still make it binary by doing some feature engineering. Definitely we do some amount of information in this process, but that is fine if at all we want to solve that particular problem by using MP neuron. Okay, so the one feature which we are considering here is launch within 6 months, and it can be 0 or 1. The other variable we consider is whether my phone is light or heavy, right? So Again, that can be represented as 0 or 1. We also think about the screen size, right? We think whether the phone is dual SIM or not. We think about the memory configurations, right? We think about battery, we think about pricing, right? But all these features that we think uh, when we talk about the phone specifications, we can binarize it, right? So these are the potential options you are having, right? So this is the data about the phone, about the various options of phone which you are considering. Okay, and after gathering all this data, after some thoughtful uh, process, you think that maybe this phone is the potential buy for you. Maybe this phone can be also one. So now we try to narrow down our search, right? And you say that this phone number 1 is the one which you liked, phone 3 you liked, phone 5 6 you liked, 7 you liked, right? So this data that you have generated, okay, now you can apply MP Neuron, you know, which can learn from this data, which can learn about your like and dislike based on the phone feature, right? And next time if somebody give this specification about some other phone, then the model can say that you like this phone or not, right? So my point is, the model which we have just learned, this model which we have just learned, if we'll fit this model to this data, it can learn from this data and it can predict whether you like a particular phone or not if the person will give you these specifications, right? By now you must be clear that NP neuron is only capable of dealing with Boolean input and Boolean output, right? Okay, so this was a question which I was going to ask, and I have answered it myself. So let's move ahead. Let's check the next question. Okay. Okay. So now we understood our model. We understood the kind of data that we'll be dealing with this MP neuron. Now let us see what is the loss function. Okay. How would I learn from that data? Okay, but before that, let us see what is a loss function. Okay, so this is the data that you have gathered, and this is your target output. 1 means you like that phone, 0 means you did not like the phone. Now you have created a model that is capable of making prediction on those phones, right? And these are the predictions. So this was the phone which you like, but model said that no, you will not like this phone. So he said that it will be 0. This is the phone which you did not like, and model said that yeah, you will not like this, you will not like this phone. This is a phone which you liked, and model also said that you will like this phone. So this is a row of your like, and this is the row of model prediction, right? Now how would you con, uh, uh, come up with a decision that this particular model is good or bad, right? You need to come up with some metric, right? Then only you can judge the performance of model. Now one thing note here, still now we haven't learned how to uh, learn, I mean how to train a model. We are just assuming that we have created a model and the model is making this prediction. Okay, and now we are trying to assess the performance of that model, right? So to assess the performance of model, we are having a metric called loss function, right? And what is that loss function? This loss function is nothing but the difference between the actual label and the predicted label, right? So in this case, uh, what is the loss here? The loss. So this is a case where model has failed to make the correct prediction, right? And this is the another case where model has failed to make right prediction. This is the another case, right? So I think there are three cases where model is not able to make the correct prediction. Am I right? So out of the total, I think there are total four, four, eight. Out of total eight, out of total 10 observations, there are three observations where model is not able to make correct prediction. So the accuracy would be what? 7 upon 10, 70%. So out of, 100 times, your model will be able to make correct prediction 70 times. This is how you calculate the accuracy of your model, right? Now, we said that the loss will be the difference between your actual label and uh, predicted label, right? Now, let's make certain adjustment to that. Instead of saying just the plain difference between these two, we take the square of difference. Okay. Now, the reason for taking the square of difference is, what may happen is here it is 1 and here it is 0. But if what would happen if here it is 0 and here it is 1, right? What will happen is, in this particular case, the model, I mean, the summation of loss will become 0 because here the sum will be 1, here the sum will be -1. So effectively it becomes 0. It will say that your model has able to identify all the cases, but it has actually not able to identify any of the cases. The positive one can cancel the negative one. So that is the reason we, instead of taking the plain subtraction, we take the square of difference, right? Now you might ask a question, if that is a problem, if the problem is the square, the positive ones can cancel the negative ones, then why don't we take the absolute difference? The reason we don't take the absolute difference, actually we can, but we do not prefer to take the absolute difference, is the absolute difference function is non-differentiable, and you'll get to know how much it is important for us to have a function which is differentiable, because it would make our life much easy when we'll go move ahead, right? So we, in a nutshell, for now you can understand that we would prefer to have a function which is differentiable, and this function, this square difference function is differentiable. So this is a desirable function. Practically you can take the absolute difference also, but that will make your life miserable when you'll go to the algebra part, right? Which we'll see a bit later also. But for now, you can just understand that the reason for taking the square difference is the square difference function. First of all, it will avoid that problem. It will avoid the cancellation of -1 and +1. The second is the square difference function is differentiable. Is it clear?
Yes.
Okay, awesome. Now try to attempt this question. I want the answer of this question in 2 minutes. Just now we have covered this. Quickly tell me what would be the correct answer for this question. L1 loss is given by mod of y minus phi cap, and L2 loss is given by y minus phi cap square. Given that the both losses are positive, why L2 loss is more preferred in deep learning than L1 loss? Okay. Now, before we attempt this question, let me quickly tell you, this loss function is called L2 loss, right? Why L2 loss? That 2 comes from this power. This is the square difference, right? So that is why it is called L2 loss. If I would have taken the absolute difference between yi minus phi I cap, it would have been L1 loss. So the question is very straightforward. It is saying that in deep learning, why do we prefer to have L2 loss function compared to L1 loss functions? So now you can look into the options and quickly give me the answer. Anyone?
I think it is difficult to train using L1 laws.
Absolutely. Absolutely. You're absolutely correct. Correct. And the reason is, what is the reason why it is difficult to train using L1 laws? Because it is not
Because of
differentiable,
the
non-differentiable, right? Absolute difference,
yeah.
the absolute function is not differentiable function. That is why it is difficult to train using L1 laws. Okay. I'm glad that you have been able to follow till this far. I know it's not very easy uh, to directly jump into the deep learning topic and understand the mathematic aspect of it. People used to do deep learning just by invoking the required packages and get the answers, but they don't know what is actually happening at the behind. If we'll follow this approach, I'm pretty much sure that you will be able to understand the backend processing of complicated deep learning packages. So kudos to that, and please keep it up. Okay, now let us come to the very important part: how to train our model. Okay, so right till now our assumption is we have trained our model and we were able to generate the predictions. Now let us see how to actually train the model. Okay, and I have said that this is the main function. This is the main hypothesis function of MP neuron, and the only threshold part is the only part which we need to learn. If we are able to figure out this optimal value of b, then we will be able to say that our model is learned and we can make the predictions on unknown data, right? So learning of MP neuron model is as straight as finding the optimal value of this b, which is threshold. Okay, and you know the one of the very commonly used practice to get this optimal value of b is to use brute force approach. you know Although this is not a very niche technique, but since MP neuron is not practically used anywhere, this is just to lay the foundation block of future classes. We are seeing MP neuron, but till now people use brute force approach for MP neuron, for training an MP neuron model. Okay, now let us see what is this brute force approach is. So what happens is we have to identify this optimal value of b, right? What is the lower cap of this threshold value? Can anybody tell me what is the minimum value the variable b can take?
1.
Yes, one it can take, but I think it should be 0. The minimum value b can take is 0. How it will be 0? If
Yeah, because
Mhm.
okay.
Yeah,
No, you say
okay,
because binary it is a binary number.
yes. So it since it can only deal with binary inputs, if all of my input feature is 0, in that case b can take value as 0, right? If all of my input feature is 1, let's say I'm having 5 features, right? If all of my input feature is 1, then the maximum value of b can take is 5, which is equivalent to number of features. So the optimal value of b, it would be always between 0 and n, where n is the number of features, the number of input features. Okay, agree to this point?
Yeah.
Cool. Now within this search space, within between this 0 and n, we have to identify the optimal value of b. What we'll do is we'll apply a brute force approach here. First of all, we'll set the value of b equal to 0. Okay, now what will happen is here first of all we will do the summation of this, right? So what will be the summation of this particular column? It would be 4 plus 1, 5. Is 5 greater than 0? No. So your prediction will be 0, right? Here your prediction will be 0, but actually it was 1. So here our model has made mistake, right? You make the sum of column 2, 1, 2, 3, 4, 5, right? So your summation is 5. 5 is greater than 0, right? Here 5 is greater than 0. That means what? The output will be 1. Your actual value was also 1. So we have made the correct prediction here. Let's take a step back. Here I said that it will be 0, right? It won't be 0, it will be 1 here also, because the summation is what? 4, 5. 5 is greater than 0, right? So this condition is satisfied and my output will be 1. So here also I have made correct prediction. Here I also have made correct prediction. Here also I'll make correct prediction, right? But here it will fail. Here still the summation is 2. 2 is greater than 0. The condition is fulfilled. My prediction will be 1, but actually it was 0, right? So out of total 10 cases, it will be able to make correct prediction for 6 cases. For 4 cases, it will fail. And what are those 4 cases? These are the 4 cases: 1, 2, 3, and 4, where your like was 0, but still somehow the model will make prediction as 1, because this sentence, this expression will get satisfied, right? So when my threshold, when my value of b was 0, my loss was equal to what? 4, right? So this is what I have shown here in the graph. Now let us set the value of b equal to 1, right? So if my b equal to 1, again I'll repeat the same process, right? And then I'll see how many losses or how many mistakes I'm doing. So when my b is equal to 1, I'll be making total 3 mistakes. Okay, so my loss is decreased. Now I'll set the value of b equal to 2, right? Again, I'll repeat the same process and I'll check how many mistakes I have done. When I have set the value of b equal to 2, I'll make total 2 mistakes, right? So similarly, I'll keep on changing the value of b from 0 till n, and you will see that the minimum number of mistakes I will be doing, the minimum number of mistakes which I'll be doing, which is equal to 1, is the case when my b is equal to 5, right? So we have to identify that particular value of b which will give me the minimum number of mistakes. Okay, so with this brute force approach, I'm able to figure out that if I'll keep my b equal to 5, I'll be making minimum number of mistakes. So the optimal value of b comes as 5, right? So you have learned the MP neuron model. You have identified the optimal value of b. You have learned the MP neuron model. Okay. Now, if somebody comes and give you a fresh mobile specification, he gives you these uh, data about these parameters, right? So it's very straightforward. It's very simple, right? You just need to do the summation of the input. You need to check whether if it is greater than the optimal value of threshold. If it is greater than, you will like that phone. If it is not greater than that threshold, you will not like the phone. So you will be able to make predictions on new data. Is the algorithm clear to you? Any questions? Any slight confusion?
So, Ashutosh, the prediction algorithm uses only this formula, or is there other ways also to train?
For now, you can just understand this is the only formula we have for training the model. We will keep changing the value of b, and we will count the number of mistakes that we have done. We will stop our process in that particular value of b where my loss or mistake is minimum. So with this approach, we have identified that b equal to 5 is the value of threshold we should keep, which will give me the minimum number of mistakes, that is equal to 1. Right? Now the same thing, so whatever thing that we have discussed verbally, the same thing you can achieve using, by using Python. So this is the code I have written for that. So first of all, I have created the data part, right? So this is the specification of your first mobile, and this is the target variable. 1 means you like that phone, 0 means you did not like the phone. Right? This is the specification about your mobile 2. 1 means you like the phone, 0 means you did not like the phone. Similarly, you are having the record of 10 mobile. You use this data to get the optimal value of b, and once you have learned the optimal value of b, you can use the expression to compute the target variable on future data, right? So this is the Pythonic implementation of the algorithm that we have discussed. I'll share the notebook with you. You can check by yourself also. You can go through line by line and see how this code is working, right? But I think all the elementary concept required to understand this code is what we have already covered, right? So I'm hoping that there won't be any issue understanding this code. All right, now let's go to another question. Quickly look into this question and answer me what would be the correct option. Why is the brute force method to find a threshold of MP model not feasible recommended approach? Just think a little bit and tell which will be the correct option. Just now we have seen the brute force approach, right? But this brute force approach is not the best technique.
Third.
Yes, absolutely. And how it is not scalable? So what we are doing here is, we are applying a for loop. We are changing the value of b one after the other, right? What will happen if you are having a huge number of input feature? Let's say that I give you some data around DNA, right? So typically in machine learning or any data science problem, this DNA data is identified as a high dimensional data, right? And you have to identify that that particular DNA is the normal DNA or it's an anomaly, right? So if you are having like thousands number of features, you have to keep on doing this operation thousand number of times, right? Right. The point which I'm trying to bring here is, if suppose you are having 10,000 number of input features, the optimal value of b can be any integer between 0 and 10,000. So you have to run this for loop for 10,000 number of times to get the optimal value of b in worst case scenario. Okay, so this is not scalable approach. All right. Okay, now we have learned how to train a model, or we have identified how to check the performance of model also, right? Now let's see this case. How do we evaluate the model performance? So you have trained the model. Now you will be making predictions, right? So these are the 4 new data. These are the 4 new specifications about 4 phones. This is the specifications of phone 1. This is specification of phone 2, 3, and 4, right? And with the help of your learned model, you identified the predicted values, right? So what you will do is, you will check for how many times your prediction was correct, right? So accuracy is nothing but a fraction of times your prediction was correct. So here the accuracy is 75%. So out of 4 observation, for 3 observations your prediction was correct, the accuracy is 75%, which is an indication that your learned model is working well, right? Okay. So we learned about the hypothesis or the function of model. We learned about how to train it. We learned about how to check its performance. In the next class, we will see the geometric interpretation of